In this last section, we're going to be looking at logarithmic and exponential functions again, but in this particular case, we'll be focusing on the logarithmic and exponential functions with bases other than e. Particularly, let's go ahead and look at some examples of the generic b for our base. So these are some formulas that you'll want to know. The derivative with respect to x of b, and b is any number, it's not a variable, it's a number, to the u of x. U of x means any function, let's say like x squared, cotangent x, something like that. The derivative of that expression is b to the u of x times the natural log of b times the derivative of u of x. So again, it's b to the u, natural log of b, u prime is how you'd look at that. We can also look at the integral. Let's go ahead and look at the integral of b to the x dx. That's going to be 1 over the natural log of b times b to the x plus c. Now this is only if the exponent is x. What if that was something like an entire function? So more commonly you might see something like b to the u of x dx. We have to do our u substitution and make sure we have our du here, if this is the case. And if I have all those components in place, this is 1 over the natural log of b times b u of x plus c. So these are some important formulas that we need to know for now. We'll also add some more to the list in this section a little bit later, but let's go ahead and work some problems using these. So to get started, we'll start with some basic ones. Let's look at the integral. Actually, let's start with derivatives. Let's look at the derivative with respect to x of y equals 17 to the x. So that would be 17 to the x. Well, we're going to use this first formula up here, and if you notice, my function is just x. So that's equal to 17 to the x, natural log of 17 times the derivative with respect to x of x. And this is that u prime of x. Well, simplifying, we get 17 to the x, natural log of 17, and the derivative of x is just 1. And of course, multiplying by 1 is a multiplicative identity, so we could just rewrite this as 17 to the x times the natural log of 17. So this is my derivative, which of course is the slope of the tangent line at any point along the graph, at any defined point along the graph. I want you to make sure you're careful when you write these. If we have this written as natural log of 17 times 17 to the x, this gets a little bit confusing. 17, you might think about multiplying these, and that's not really appropriate because the log argument is just 17. So that's why we usually like to pull that out front. So be careful about how you write those. Make sure you're using parentheses around the arguments of your log functions. Let's go ahead and look at another one. Let's look at the derivative with respect to x of 6 times, we'll use the dot to represent times, 11 to the x. Now this is, even though we're multiplying, this is not a product rule. This is just a coefficient that we drag along. So 6 I drag along, and then I take the derivative of 11 to the x. The derivative of 11 to the x is 11 to the x, natural log of 11, times the derivative of x. So again, we're dragging along that 6, 11 to the x, natural log of 11. The derivative of x is 1. Now I'm not multiplying 11 times 1. The 11 is the argument of my log function, and I can't do anything with that. I can't include anything in it. So when I rewrite this, I have to be very careful. So that's why we like to write it as 6 and then parentheses 11 to the x. So we don't multiply 6 times 11, exponent comes first here, times the natural log of 11. So be careful when you're writing these and when you're inputting your formulas or your equation solutions into MyMathLab or your calculator, because it is very sensitive about what's being multiplied. For our next one, let's go ahead and look at something that actually is the product rule. Let's look at the derivative with respect to x of x to the 5th times 8.6 to the x. So this is a product rule. This is a product rule. The other one wasn't, because this is a variable times a variable. So product rule. So our first step that I'm going to do is I'm going to go ahead and write everything out here step by step. So this derivative is equal to the first function times the derivative of the second function plus the second function times the derivative of the first function. Now when I get done rewriting these are not usually very easy to work with. x to the fifth, of course I'm dragging along. The derivative of 8.6 to the x is 8.6 to the x, natural log of 8.6, times the derivative of x, which is 1. Now remember, I'm not multiplying 1 times 8.6. I'm taking 1 times all of this. Next I have 8.6 to the x, and the derivative of x to the fifth is 5x to the fourth. So here's my simplification. Now when I'm looking at this, I think I can pull out an 8.6 to the x, and I think I can also pull out an x to the fourth. So 8.6 to the x to the fourth, that's going to leave me with an x here, x ln of 8.6 plus 8.6 to the x. Everything else is factored out, so that leaves me with a plus 5 there at the end. So again, we can apply the product rule, quotient rule, chain rules to these. The only thing that I need to make sure about is that new rule, that new derivative that I have. Let's go ahead and look at one that's not so obvious what we need to be working with. This is 4 to the 2x plus 4 to the x minus 56 equals 0. So this isn't a derivative. Let's look at this and think solve. So we're trying to solve for x. So this is 4 to the 2x plus 4 to the x minus 56 equals 0. Now we're used to like x squared, not 2 to the x. You know, we're used to the exponent being just a coefficient or a constant of some sort, and the base being our variable. I think when we're looking at this, one of the easiest things that we could probably do is a substitution here. You know, unless you see the direct way to factor this, I think a substitution will help. So for this substitution, let's let a equal 4 to the x. And I'm choosing that because that's my linear term here. So if a was equal to 4 to the x, this first term would look like a squared plus a minus 56 equals 0. This of course factors into a plus 8, a minus 7. So a plus 8 equals 0, and a minus 7 equals 0. Solving for a, I get a equals negative 8. Solving for a, I get a equals 7. But those are not my answers. I have to sub back in. So a is 4 to the x. So this simplifies to 4 to the x equals negative 8. And 4 to the x equals 7. So if I want to figure out what x is, I need to solve this, and there's many different ways that I can do this, but the easiest way is to probably take the ln of both sides. So when I take the ln of both sides, I'm going to scoot this negative 8 over a little bit. Something interesting happens here. I can't take the log of a negative number. So this piece is undefined. There's no graph over here. There's no natural log of a negative 8. So for this one, there's no solution. Now let's come over here and look at this side. I would take the natural log of both sides. So natural log of 7, I think, is what we had there. So the reason I take the natural log is because the x pops out front. So I'm left with x ln of 4 equals ln of 7. And again, I'm trying to solve for x, so I divide both sides through by ln of 4. And then when we divide, I get x equal ln of 7 over ln of 4 as my solution. Now, we need to keep looking at this and simplifying it if possible. I don't see anything that will cancel. I don't see anything that can simplify. I guess I could take this 4 and rewrite it as 2 squared and pop the 2 out front, but I don't really see a benefit to that. I don't see that it's going to end up canceling with anything. So this would be an example of solving by substitution. Here's my solution. If you want to graph this and check it, you could. You're going to have a decimal approximation. Your calculator won't pop out ln of 7 over ln of 4. Now let's go ahead and recall what a derivative is. You're going to have to work some story problems or application problems, and they ask you to find the rate of change. So let's recall that the derivative is the rate of change. So when you're asked to find the rate of change, you would take the derivative and evaluate it. It's also the slope of the tangent line. So these are two different applications of the derivative. So rate of change, keep that in mind because you will run across some problems that ask for the rate of change specifically in your homework set. Now when we're continuing on, let's go ahead and start looking at integration. So the integral of, let's say, 5 to the 2x dx. We have to use a u substitution here. So we let u equal 2x, du is 2 dx. So I have the dx, I need a 2, so I'm going to multiply by a 2 on the inside, compensate with a 1/2 on the outside, and I'm left with 1/2 the integral of 5 to the u, 2x is u, 2 dx is du. And now this follows straightforward from my formula. So my formula would say this integrates to 1 over the natural log of 5 times 5 to the u. And of course we need to switch this back to x's. So this is 1 over 2 ln of 5, 5 to the u. U is 2x plus c then. So there's my integral. This is the antiderivative. So when we're working through with these problems, we always want to make sure that we simplify. Now I notice for this one, we could simplify it a little bit. We could also rewrite this in another form. Let's look at 5 to the 2x. 5 squared is 25. So this is the same in the numerator as 25 to the x. And in my denominator, I could pop this 2 up to the 5 squared, and I'd be left with ln of 25 plus c. So I like this one a little bit better. This one's a little bit cleaner, a little bit easier to read, and a little bit easier to work with. So if you can simplify, go ahead and make that effort to simplify because it makes things a little bit easier to work with. Let's go ahead and look at another example where we're looking at a definite integral this time. This last one was indefinite because I didn't have limits of integration. Let's look at the integral from 1 to 3 of 1 plus the ln of x. And again, put parentheses around the arguments of your trig functions, please, times x to the x dx. Now this x to the x, that's a variable to a variable. So that one's a little bit different. Now this is definitely going to need some u substitution. So as I'm looking at this, I'm thinking we're going to have to rewrite this somehow. It would really be nice if somehow I had this with some e's involved, because the integral of e to the u du I can work with. I don't know how to integrate log yet. So let's look at this x to the x. If I wanted to, I could rewrite this using my rewrite for our bases here. So this would be e to the ln of x to the x. Okay, now the reason this works is the ln is log base e and this base is e. So this is a quick little rewrite that I can look at. Now this x I can pop out front. So this is e to the x ln of x. So let's go ahead and rewrite our integral using that. Now I haven't done a substitution, so my limits of integration are still the same. So I have 1 plus the ln of x, and then e to the x ln of x dx. Okay, so now let's try our u substitution. Let's let u equal e to the x ln of x. Well, actually, let's not have the e in there. Let's just have it be the exponent, so that's an e to the u. So x ln of x. Now my du is going to be the product rule. So I have the first times the derivative of the second plus the second times the derivative of the first dx. So the x's cancel and I'm left with 1 plus the ln of x dx, which is what I wanted. So here's my 1 plus ln of x, here's my dx. Now when I rewrite this, I need to make sure I either change or drop my limits of integration. Doesn't matter which. So this would be e to the u du. Now my limits of integration, they're not going to be real simple limits of integration here. If I take my value for u is equal to x ln of x, that would be 3 ln of 3 and 1 ln of 1. And ln of 1 is 0, so that would be an easy enough one. But I think I want to convert back here when we get done. I don't want to change my limits of integration right now. So I'm going to drop them. And we know the integral of e to the u is e to the u, but I need to convert back to my x's. U is x ln of x. So if we want to look at that and rewrite it, that would be e to the ln of x to the x, which is just x to the x, and that's evaluated from x equal 1 to x equal 3. And again, the important part here is I use this rule to be able to rewrite. Now plugging in, remember you always do your upper minus your lower. If I plug in my upper, I get 3 to the third, lower minus 1 to the first. 3 cubed is 27 minus 1 is 26. So that's kind of a tricky one, but it's an interesting problem. So make sure that you kind of stick with it and use this idea of that rewrite to get yourself started. Now the next problem we're going to do is we're going to think about writing the equation of a tangent line. So again, writing the equation of a tangent line we can do if we can just figure out the slope and a point. So let's find the equation of a tangent line. I should say of the tangent line, because we're going to be looking at a specific point. To the graph of f of x equal x to the cotangent of x. And let's do this at x equal 1. Well, let's right away look at something here. If we know x is 1, let's figure out what y is. So this implies that y would equal what? So if x is 1, the cotangent of 1, I don't even really know what that is. It's the cotangent of 1 radian. That's not part of the unit circle that I know, none of the standard angles that I know. But I do know that 1 to any power is going to be 1, so this tells me that y is also equal to 1. So the exponent is some constant, cotangent of 1. 1 to the cotangent of 1 is just 1. So here's my ordered pair that I'm going to be working with. Next I need to figure out my slope. And to figure out my slope I need to take a derivative. So if we look at the derivative, I can do logarithmic differentiation on this, or I can rewrite it kind of like I've been working with before in rewriting this with the definition of e. So I could use logarithmic differentiation, and that was from our previous section. I think this would be a good one to do logarithmic differentiation on. Or I can use a rewrite. And the way we would rewrite this would be x to the cotangent of x is equal to e, I have to be careful how we write this, ln of x to the cotangent of x. Now remember, one of the reasons we like to do this is so the cotangent of x could pop out front. So this would rewrite again to e to the cotangent of x ln of x. Okay, so that kind of gives us a start as well. It doesn't really matter for this particular case which method I use. I'll get the same answer in the end. I'm going to stick with the rewrite because we've already done some logarithmic differentiation type problems. So I'm going to start with this idea. So to find the derivative, I could use logarithmic differentiation or rewrite and then take the derivative. So f of x, we decided, is going to be equal to e to the cotangent of x ln of x. My derivative then, the derivative of e to the u is e to the u times the derivative of u. And the u is basically just that exponent. So that's cotangent of x, natural log of x. So I haven't found my derivative yet. And you can tell that these problems get kind of ugly. When we get to evaluate them, they'll get a little better. So this is a product rule, so I'll have the first times the derivative of the second. The derivative of the natural log of x is 1 over x, plus the second times the derivative of the first, and the derivative of the cotangent is negative cosecant squared of x. So there's my derivative. It's not really easy to work with, so let's go ahead and simplify it a little bit if we can. And by that I just mean like pulling out negatives. So this would be cotangent of x over x. We can't cancel the x's because this x in the numerator is part of my trig function. Okay, minus ln of x cosecant squared of x. So there's my derivative. Now I need to find the slope. So in order to find the slope, I need to take my derivative and evaluate it at x equal 1, because that's the value that was given up here. So this would be e to the cotangent of 1 times the natural log of 1 times the cotangent of 1 over 1 minus the natural log of 1 times cosecant squared of 1. So I've got everything plugged in. Now we can start evaluating this. So f prime of 1. Natural log of 1 is 0. So this natural log of 1 is 0. 0 times cotangent 1 is 0. E to the 0 is 1. Okay, so that starts this first part. Cotangent of 1, that's just some value on my unit circle. I don't know what 1 radian, I don't know its cotangent. So this is just cotangent of 1 over 1 is cotangent of 1. And again, the natural log of 1 is 0, so this whole term goes to 0. So it looks like to me my slope is the cotangent of 1. So writing the equation of my tangent line, I would use my slope of cotangent of 1, and I would use my ordered pair that's 1, 1. So this would be y minus 1 is equal to the cotangent of 1 times x minus 1. So this would be my equation in point slope form. Now if I wanted this in slope intercept form, then I would go ahead and solve for y. I'm going to do that in 2 steps. This is cotangent of 1 times x minus cotangent of x, and then I'd have to add the 1 to both sides. And again, whatever you do to one side, you have to do to the other. So the last step for simplification would be y equal cotangent of 1 times x minus cotangent of x plus 1. Okay, so that's the equation of the tangent line at that point. It doesn't look very easy to work with, and you're right, it's not. But what the important part is that we have the slope, and then this y-intercept would be negative cotangent of x plus 1. Now I don't multiply 1 times x. This is the cotangent of 1 is my coefficient, and then x is my variable piece. So that's kind of where we'll stop with the derivative of e to the u, or sorry, not e to the u, but a to the u or b to the u of x, and also the integral. And what we want to look at now are the logarithmic, so the log base b instead of the natural log of e or the log base e. So let's go ahead and focus on logs in our next section. So when we're talking about logs of different bases, the one we looked at before was log base e of x, for example, which was the natural log of x. We could also have log base 10, which is also known as the common log. And when we see log base 10, we don't rewrite that as a base 10, we just usually write log of x, and it's an implied base 10. So these are some different types of logs that you'll see, and you can actually see any value here that's an integer. So let's go ahead and look at some characteristics of logs. For instance, we know that if we have an exponent in the argument of a log, for instance log base b of b to the x, let's say, I can pop the x out front and I'm be left with log base b of b. And log base b of b is just equal to 1. So x times 1 is just x. And so that's another way that we can rewrite this. And this would be true for all x. So there's a little characteristic that's kind of nice to be working with. A couple other things. B to the 0 is 1. Don't forget that. Also log base b of 1 is equal to 0 because b to the 0 equals 1. I need to be able to rewrite these. So in exponential form this would be b to the 0 equal 1. A couple of other quick notes. If I have b to the x, that works really great for an exponential function, but b cannot be equal to 1 because then I just have 1 to the x, which is just be 1. So when we're flipping these back and forth and rewriting these are some things that you might come across. Now when we start talking about derivatives, we can also start talking about antiderivatives, integrals, but not quite yet in this particular section because we need to be able to get things into a form that allows me to integrate into an antiderivative. So we're going to focus mostly on the derivatives in this particular case. So let's go ahead and get started with some formulas. Let's look at the derivative with respect to x of log base b of x. The derivative of log base b of x is 1 over x natural log of b. Now this is only going to be true for x greater than 0 because we know from our previous work that the argument of the log has to be greater than 0. So there's a nice little derivative we could look at. A lot of times we end up looking at the absolute value when we're talking about the log base b of the absolute value of x because we force this to be positive so we can actually work with the log. This is going to be equal to 1 over natural log of b. And this is true for any value of x except x cannot equal 0. So if I have the absolute value signs here, that kind of helps me out a little bit. Now this argument up here was just x and so was this one. What if we had an entire expression? For instance, log base b of u, meaning u is some function of x. This is 1 over u natural log of b times the derivative of u. Now a lot of times before we used to write u of x, and you could write that here as well. So this is an important formula to know. And then I also have a way I could rewrite. So this is not a derivative, but if I have something like log base a of u, I can rewrite that in natural log or a conversion form. This would be the natural log of u over the natural log of a. It'd also be log of u over log of a, or any log base. So these are some important formulas that will come in handy when we're starting to work with logs of different bases. First example, let's go ahead and look at the derivative with respect to x of 5 log base 3 of x to the 4th minus 8. Now this is not the product rule. The 5 is just a coefficient, so I drag it along. So my derivative, and I'm just going to follow along right up here, log base b of u, this would equal 1 over u, natural log of the base, so 1 over u, natural log of 3. Now I need the times the derivative of u, which would be 4x cubed. I can definitely simplify this. 5 times 4 is 20. So I have 20x cubed all over x to the 4th minus 8 natural log of 3. There's my derivative. Now again, this is the slope of the tangent line at any point along the curve. It still has all those same meanings that the derivative always has had, and it's also the rate of change. Okay, let's go and look at a few more examples. Let's look at the derivative with respect to x of 3 over log base 8 of x. Now before I can take this derivative, I think I should probably rewrite it. I could use this as a quotient rule right here, but it might get a little ugly. I think it would be easier to flip this and use a chain rule. So let's flip this up top, and when we do that we have a negative 1 in my exponent. Now this is not x to the negative 1, this is the entire log. So this is a chain rule. I'd bring the negative 1 down, and I decrease the exponent by 1, and now I'd multiply it by derivative within. So this is 1 over natural log of 8 times the derivative of x, which of course is 1. This needs a lot of rewrite. So again, this is y prime. I better note that. So this is equal to negative 3. And then everything looks like it flips down into the denominator. So negative 3. And then this log flips down. So this is log base 8 of x, quantity squared. And then over here, I have this that also goes into the denominator. So this piece is x ln of 8. So there's the derivative, but we have a little bit of an issue here. We have log base 8 and log base e mixed together. So let's go ahead and rewrite this using our rewrite that we looked at above. Log base 8 of x, that would be the natural log of x over the natural log of 8, quantity squared. And then of course I have x natural log of 8 here as well. Rewriting, I have the natural log of x. Whoops, that's going to go into the denominator. I have the natural log of x squared, natural log of 8 quantity squared times x natural log of 8. Now this is not a times sign, that's actually the variable x. Now as I keep simplifying this, the natural log of 8 cancels with one of these. When you divide by a fraction, you're multiplying by the reciprocal, so this natural log of 8 is going to pop up top. And that's all over the natural log of x, quantity squared. It's not x squared, it's the entire function of the natural log of x squared. So there's a nice little way that we can simplify this and rewrite it a bit. And I forgot the x here, so I better make sure I include that. That x came from right here. I don't like to combine different log bases. We usually like to just have one base, whether it's e or whether it's 10 or some other. We don't like to combine different types of bases if we can help it. So that one was important to be able to simplify. Let's go ahead and keep working through a few problems. We could look at a second derivative even. We could look at the second derivative with respect to x of 6 log base 2 of x minus 4. Now before we even got started, if we wanted to, we could rewrite this. So my function is y equals 6 log base 2 of x minus 4. And I could go through and take the derivatives, but if I wanted to, I could rewrite this. This is the log of x minus 4 over the log of 2. Now remember, if you don't have a base, it's an implied 10 common log. I could also rewrite this as 6 natural log of x minus 4 all over the natural log of 2. And if we can get things into natural logs, that's usually the preferable function to work with, or the preferable base to work with. So we haven't really done anything yet other than rewrite. So let's go ahead and start with a derivative. This is going to be the quotient rule. So let's start with y prime. I have a 6 out front. I'm just going to drag it along, and I have the bottom. Actually, I think I'm going to change my mind on this. This natural log 2 is a constant. So I'm going to pull out 6 over natural log of 2, and I no longer have a quotient rule. I just have the derivative of the natural log of x minus 4. The derivative of the natural log of u is 1 over u prime. The derivative of x is 1. So I get y prime equals 6 over natural log of 2. I think I'll write x minus 4 out front. X minus 4 natural log of 2. So there's my first derivative. Now my second derivative, of course, is the derivative of the first derivative. So I still don't need a quotient rule here because everything I have out front, the 6 natural log of 2, is all constant. So I'm just really left with 1 over x minus 4. So I could flip this up top and go ahead and take a derivative. So this is still y prime. So now y double prime is when I actually take the derivative. So I have 6 over ln of 2. I bring the negative 1 out front, decrease the exponent by 1, and then multiply it by the derivative within. Now from here it's a simple rewrite. So let's see what we have in here. So I have a negative 1, x minus 4 quantity squared. So rewriting as a single fraction. Looks like I have a negative 6 over x minus 4 quantity squared natural log of 2. So there's my second derivative. Of course, this would help us figure out about concavity if we were looking at curve sketching with the function. Let's go ahead and just keep working on quite a few different problem types, so when you get to your homework you'll be well prepared. If we have a function f of x equal log base 3, and then we kind of have a large argument here, 9 over square root of x plus 5. This is the argument of my log function. Really what I can do here is I could take the derivative using our log rules, or I could rewrite this using my log rules to make it easier to work with. So we'd have f of x equals log base 3 of 9 minus log base 3 of x plus 5 to the 1/2. That's the same as square root, and then I can pull the 1/2 out front. So I have f of x equals log base 3 of 9 minus 1/2 log base 3 of x plus 5. Now I still haven't taken a derivative. So far the only thing that I'm doing is rewriting. Last step, 3 to what power is 9? That's the question that's being asked here. So I could rewrite this as 2. 3 squared equals 9, so this is 2 minus 1/2 log base 3 of x plus 5. Now if I wanted to, I could rewrite this in terms of ln, or we can just go ahead and take our derivative straightforward. So when we take our derivative, the derivative of 2, of course, is going to be 0. The derivative of a constant is 0. So I'm going to put that value of 0 minus 1/2. The derivative of log base 3 of x plus 5 is going to be 1 over x plus 5 natural log of 3 times the derivative of x plus 5, which is 1. So rewriting, we get f prime of x equals, looks like just a negative 1 over 2 times x plus 5 ln of 3. So there's my derivative. Now there's several different ways I could have taken this derivative, but for this particular case that worked out pretty slick, just to go ahead and rewrite that first using the properties of logs. Now no matter which method you choose to take your derivative, whether you rewrite or take it straightforward, you should get the same answer in the end, but you may have to simplify a little bit. Now whenever you can, rewriting using those rules is better than trying to use something like a product or a quotient or a product quotient chain rule. So keep in mind rewriting. Now sometimes you have to use logarithmic differentiation. So for instance, if we were trying to find the derivative with respect to x of 3x to the 7x, there's no rules here for me to rewrite this because there's no log involved. So I would have to use logarithmic differentiation. So logarithmic differentiation comes up again in this particular section. So to work a problem similar to this, we did that in our notes for the last unit or the last section, so make sure you take a look through that to refresh your memory on that. As usual, if you have any questions, please let me know. Good luck, and shoot me a text if you have any questions. A screenshot really is helpful. And then you also have access to Pearson Connect as well. Good luck.